Hello, calculus people. Welcome to your Friday pre-recorded lesson. I want to finish off the last example we were working on in class, talk a little bit more about this interval that we get with absolute convergence and divergence, and give one more example, I think, where we apply the ratio test to a power series. So we were working on this example last time. We had the following power series where we had x minus 3 to the n over n. As n ranged from 1 to infinity. We calculated an and an plus 1, took a look at that ratio, and then what we do after we find that ratio is apply the ratio test. So we took this limit as n got really, really big, kind of noticed that the n's were going to be positive anyway, so we really only had to worry about the absolute value bars around our x minus 3. And we actually were able to evaluate the limit of n over n plus 1. So this is tending towards 1 as n gets really, really big. And so our overall limit ends up equaling the absolute value of x minus 3. Now, since we're utilizing the ratio test, we would like this limit to be less than 1 for absolute convergence. And we were able to actually solve this and get a range of x values where we know that this particular series is going to be absolutely convergent. So that's super, super nice. And of course, the opposite region, so any x values that are larger than 4 or smaller than 2, ended up being divergent regions. So that's always true. So as soon as you find your region of absolute convergence, you can kind of find the opposite regions that will give you the divergence, and then you're usually going to be stuck with 1 or 2 endpoints in this case. So we got kind of stuck with the endpoints of 2 and 4, and these happened to be exactly where the ratio test would give us something that's inconclusive. So in other words, I can't really make any conclusions about what's happening exactly at 2 and 4 at the moment, because the ratio test won't give us that information. So it very well could be that 2 or 4 could be divergent, they could be conditionally convergent, they could be absolutely convergent, but the ratio test doesn't really give us that information. So what we're going to do just to finish off this question is to take a look at those two specific x values. So we're going to actually substitute these x values into the power series, see what happens, and see if we can come up with a test that's going to let us know whether or not these endpoints are going to be convergent or divergent. So first, let's consider which one should we do first? Let's do x equals 2 first. Now let's go ahead and let's grab our power series, which is x minus 3 to the n over n. And we're going to sub in x equals 2. And that's going to give us a series that looks like this. So if I input 2, I'm going to get 2 minus 3 to the power of n. So I get negative 1 to the power of n over n, as n ranges from 1 to infinity. So when I go to sub in the endpoint, I get one of these kind of typical series that we've been kind of practicing with over the last couple weeks. Now, this is an alternating kind of series, so we might be inclined to try the alternating series test. Now for the alternating series test, remember that we want to pull out the bit that's causing our numbers to fluctuate above and below the x-axis. So we're going to pull out that negative 1 to the n, and then we're going to look at b sub n. And b sub n is going to be this, the rest of our series right here. So the 1 over n, this is our b sub n. And what we want to do is we want to see what's happening with b sub n as n gets really, really big. So let's take the limit as n gets really, really big of b sub n. And as n gets really, really big, we get 1 over something really, really big. So this limit's definitely tending towards 0. So because our limit is tending towards 0, our b sub n, we know that this particular series is going to converge by the alternating series test. Okay, so that's one of the endpoints. So one of those endpoints, we can tackle it with the alternating series test. That's nice. Let's take a look at our other endpoint. I think it was 4, yeah. Okay, so once again, we're going to grab our power series. And we're going to sub in x is equal to 4. And in this case, instead of getting -1, we're going to get +1. So we're going to get this series 1 over n. And this is a bit weird because the alternating series, -1 to the power of n over n, is convergent, yet this particular series, we've already, I think, shown that this one's going to be divergent by the integral test. And if you haven't, then this is technically a p-series. So this is part of the next quiz. This is part of our last quiz as well. This is going to be a p-series with p is equal to 1. This is going to diverge by the integral test. So we can essentially set up an integral that looks very similar to our series, our a sub n. So we're going to set up an integral 1 over x dx, and we're going to take the same bounds on our integral, and if this integral converges, then we know that that series is going to converge. But the problem with this particular integral is when I go to evaluate it, I get the natural logarithm, and we're kind of evaluating that between the endpoints of 1 and something, right? So maybe like 1 to m, for example. And when I go to input these particular boundary values into the logarithm, we're going to get the limit as m gets really, really big of the natural logarithm of something that's also getting really, really big. Of course, I'm subtracting ln of 1, which is 0, so that one doesn't really matter. But this is tending towards positive infinity. So we can show that this integral is unbounded. Therefore, our series is going to be unbounded as well. So it feels a little dirty to me that like the alternating series actually converges, but the series that doesn't alternate doesn't converge. I find that a bit weird, but such is life. That's what we have to live with based on the tests that we have at our disposal. So this particular series at the endpoint x is equal to 4 is going to diverge by the integral test. How did I summarize that? So the endpoint, and so now we can really summarize up our findings for this particular power series. So this one, we had to do a little bit of more in-depth analysis because we ended up getting an interval of numbers where it was possible to have absolute convergence. That was a little different in our first example. So if we were to scroll back up to our first example, the first example, basically the only way that this was going to be absolutely convergent was right at x is equal to 0. Other than that, this limit was tending towards infinity and we were kind of hosed. So that's why there's so much work involved with some of these power series, because sometimes we do get a full interval that we have to kind of consider, and the endpoints we have to consider as well. So let's just summarize the findings here on our real number line. So we have what we call the center point, which is r. The center point, which is 3. So this is where our power series is centered. We were able to find these boundary values of 2 and 4. Now we had basically very good values in between 2 to 4. In this green region, we were absolutely convergent. And we know that outside of these boundary values, we were divergent. So I'm just going to put D's here for divergent. And I'm going to grab a new color because we are going to need a third color here. And based on the analysis of our endpoints, it looked like the endpoint of 4 here is divergent as well. So I'm going to color that in red. So 4 was divergent. And then in blue, I'm just going to color the endpoint 2 in blue. Because it was convergent, we just didn't know if it was absolutely convergent. So there's the full analysis of this particular power series. And I think this is a good time for us to kind of step back for a second and summarize some stuff that can happen with this particular interval. And the textbook, I think, actually does a really, really nice job of summarizing what we call intervals of convergence. And so there's a nice little theorem that goes along with this. And it goes like this. If I have a power series in the usual form where I have some kind of coefficient, and then I have this power series centered at a, so x minus a to the n, then we have 3 different possibilities. The first possibility is that the power series might only be absolutely convergent when x is identically equal to a. Now, I would say this is probably the most boring case. This is what happened in our first example. And essentially what happens is if we try to define this function, essentially what we're going to get is we're going to get a sum of a bunch of zeros. So if x equals a is the only possibility, we're going to essentially kind of get stuck here with a whole bunch of zeros. And we get the horizontal line f of x is equal to 0. So I think that's kind of a boring thing that could happen. Every single power series is absolutely convergent at x is equal to a because we always get a sum of zeros. So there are more interesting things that could happen. One of the interesting things that could happen is it's quite possible for our power series to be absolutely convergent for all real numbers. So in other words, when I'm going to look at the ratio test, it's quite possible that I evaluate this limit, and this limit actually tends towards something that's less than 1. So we kind of get squeezed into having to accept all x values as possible good x values. So that could happen, and I do have an example of that one coming up after the theorem here. And of course, the last possibility is what happened in our second example, and that is that we evaluate the limit using the ratio test, and we end up with an interval of good values. I have to excuse the garbage truck noises that are going to be happening for the next few seconds. Turn those speakers up. So the last possible case is we obtain this real number that we call capital R. This is typically what the textbooks are going to use in your online resources. Capital R is called the radius of convergence. And the radius of convergence essentially is found by looking at this limit that we get when we use the ratio test. So if we were to go back to our last example here, we obtained, I believe, the absolute value of x minus 3. So this was what we got when we used the ratio test and we evaluated that limit. And we needed this limit to be less than 1. So it's exactly in this step here where I have essentially isolated the absolute value portion of this problem, where I end up with what's known as the radius of convergence. And because absolute value gives us some information about distance, this tells me essentially how far away I am from the center to where the endpoints are. So in other words, if I kind of interpret this number 1 as a distance, I have the centermost point here at 3, and then I have a distance in either direction of 1 to get to my endpoints. So this is what the radius of convergence means. It just says if I go to the centering point, which in this example was 3, and I kind of measure out a distance of 1 unit, I should get to the endpoints of 2 and 4. And so that's what the theorem is just trying to summarize here. So it says there, if this is the case, then it's going to be absolutely convergent inside of this particular interval that we make, and divergent outside. Now, another piece of terminology that comes out of this is that interval. So the interval where we are absolutely convergent is called the interval of convergence as well. Now, I believe in the textbook, the interval of convergence also does include the endpoints as well. So if we were to come back up to our last example, our interval of convergence would actually start at the number 2, and it would include the number 2 and be measured all the way up to the number 4. But we don't include the number 4 in the interval of convergence because the endpoint at 4 was actually divergent. So I want to work on another couple examples. I want to show you an example where number 2 happens, and then I believe I have one more example of number 3. So we kind of go through this process, this lengthy process of trying to find the radius of convergence and the interval of convergence. Okay, so that hopefully summarizes up some of the key ideas. Let's take a look at a couple more examples here just to finish off the class. So let's find the interval and radius of convergence for the following power series. And we're going to do 2 more examples. So the first one is going to look something like this. We're going to have, we're starting at 0 and heading up towards infinity. And we have -1 to the n, x to the 2n. And then we have it down here, actually this is going to be 2 to the 2n. And n factorial squared. Figured we would do kind of one that looks really, really awful. And remember, I'm just going to toss up here in blue, remember that we did talk a little bit about factorial notation last time. So factorial notation, what you need to know for the purpose of doing some examples in the textbook is that n factorial represents a string of multiplications. So starting at n and then decreasing by 1 until I get to the number 1. So I'm just basically multiplying all of these things together. All right, so actually maybe I'll just keep well, I'm going to maybe change to green here. I feel like green's a little bit easier to see comparative to the black. So this is a power series, and I know that a sub n looks something like this. So we already have a sub n. The hard part, I think, is going to be trying to figure out what a sub n plus 1 looks like. So what's the next term that comes after a sub n? Well, the numerator, actually, it's a little bit of a pain in the butt in both cases. So let's see. -1 to the n plus 1. And then I'm going to do something like this. I'm going to write down the 2, and then I'm going to write n plus 1. And I'm going to have to distribute that 2 through the brackets to get what I need here. And it's going to be the same down here for this 2 to the 2n. Okay, so again, just taking my n, replacing it with n plus 1. Now inside here, we're going to kind of be stuck with something squared still. And what we're doing is we're going to alter this to n plus 1 factorial. So I'm going to go ahead, I'm just going to simplify some of these brackets just a little bit so that when we go to find the ratio, it's a little bit easier to work with. So expanding through the brackets, we should get 2n plus 2. And there's not a lot we can do with this squared bit, so I think I'm just going to leave it like this for now. We will maybe interpret that squared as n plus 1 factorial times n plus 1 factorial, but let's kind of see what happens when we go to formulate this ratio. So let's get a n plus 1 over a n. And of course, we're going to be dividing by a sub n. And dividing by a sub n is really like multiplying by the reciprocal. So it's really like multiplying by the following expression. Okay, so now our goal is to try to simplify some of this stuff as best we can using our power laws. Okay, good luck. So looking at the 1, so it looks like our negative 1s are kind of going to cancel. I'm going to be left with a copy of -1 up at the top. Our, let's see, 2 to the 2n. So this and this should cancel, and I should be left with 2 squared at the bottom. Looking at the x's, these are going to cancel, but we're going to be left with an x squared up at the top. And that's all I'm going to do for now. I'm going to deal with the n factorial and n plus 1 factorial in a hot second here. So I am going to interpret n factorial squared as n factorial times n factorial, or 2 multiplied copies of n factorial. And I'm going to do the same thing in the denominator too, because I'm going to have to expand these out and maybe do a little bit of cancellation. Okay, so I'm just going to kind of keep trucking away here. Okay, so here's my first n factorial, and here's my second n factorial. Okay, 2 squared is 4. And now I'm going to have to expand these n plus 1 factorials as well. So we're going to get n plus 1 times n minus 1, etc., all the way down to the number 1, and the same thing for my next one. So we get an n plus 1, then we multiply by n minus 1, and we keep going until we multiply by 1. And once we kind of expand out these expressions, we're going to notice that most of this stuff is going to cancel off. So all of this should cancel it with all of this and give us 1, and kind of the same thing happens over here. So when all things are said and done, in the numerator we have left over -1 times x squared. In the denominator we have 4, and we're going to have n plus 1 squared, 2 copies of n plus 1. We could expand that out maybe just quickly right now and kind of see where that goes, but it doesn't really matter, I guess, because we're going to be evaluating the limit as n goes to infinity anyway. So let's go ahead and do that. Let's actually apply the ratio test. Yeah, if you had expanded this, it shouldn't change your overall final answer. This limit is still going to tend towards 0. So let's see why that's the case. Okay, so let's take the absolute value of this monstrosity that we obtained here. And the first thing I want to do is just kind of consider what's going to be positive, what's going to be negative. I essentially want to figure out where to distribute the absolute value bars. Now, realistically, the only number that could be negative here is the x. Well, even the x squared is going to be positive, right? When I take something and I multiply it by itself, I always get a positive number. So the only thing here that is negative, technically, is this minus 1. So I can probably actually get rid of these absolute value bars just by changing the sign of the minus 1. So if I kind of get rid of this minus 1, I know that x squared is going to be positive, I know that 4 is already positive, and I know that n plus 1 squared is going to be positive as well. So we should be able to drop those absolute value bars just by kind of removing that negative 1, because it's going to turn into a positive 1 anyway. All right, so now we want to figure out what's happening as n gets really, really big. And obviously, looking at our denominator here, as n gets really, really big, the denominator is going to get really, really big, and it really doesn't matter the value of x. This fraction is going to tend towards 0. So it really doesn't matter what we were to put in for x, because the limit really only is telling us what to do when n gets really, really big. And as n gets really, really big, those denominators are always really, really big, no matter what that parameter is for x. So this limit's going to tend towards 0. Now, remember that according to the ratio test, for absolute convergence, we want this limit to be less than 1. But the limit that we evaluated is already less than 1. It's 0. So since this limit is already less than 1, all values of x will work. All values of x will be absolutely convergent. There are going to be no values of x where we diverge, because the ratio test tells us that this limit always tends towards 0 no matter what. So, in summary, we might want to write down a couple of different things. We might want to write down the radius of convergence. And we might also be interested in the interval of convergence. Now, the radius of convergence in this case, we're often going to use the symbol infinity. We're just going to say that this radius is unbounded. This radius is as large as we want it to be. And that means that our interval of convergence is also as large as we want it to be in both directions. So it's unbounded in both the negative and positive direction. Essentially, we could also write it as x can be any real number. That's another way to write this. So our interval of convergence is all real numbers. So this is essentially, for how nasty this power series looks, it's actually a very, very nice behaved kind of power series. It actually converges no matter what kind of x value we pick. Okay, so let's finish off today with one final example. And that power series looks like this. So we're going to go 0 to infinity. We have negative 3 to the n x to the n over root n plus 1. So as always, this is a power series. We would like to apply the ratio test to this. So we're going to go ahead and try to calculate a sub n plus 1, and then try to figure out that ratio that we need in order to calculate our limit. So this one's a little bit easier because it doesn't involve any kind of crazy 2n's or crazy factorials. So a sub n plus 1 is just negative 3n plus 1, x to the n plus 1. And inside the square root, we're going to get n plus 1 plus 1. So we get n plus 2 underneath the square root. And so let's go ahead and actually calculate this ratio and see if it's going to simplify a little bit for us before we actually apply the limit. So writing down our a n plus 1. I'm going to interpret again that division sign as a multiplication by the reciprocal. So remember that this up here is actually a sub n. So I'm going to multiply by the reciprocal of a sub n. And then from here, we just want to try to tackle this as best we can utilizing our exponent laws. So I can't really do too much with the square roots, but I can do a little bit of work with the negative 3's. So I'm going to be stuck with an extra copy of negative 3 in the numerator, and it looks like the same thing's going to happen with the x's, right? So I'm going to get stuck with an extra copy of x up top. So simplifying this, we end up with something that looks like negative 3 times x times n plus 1 under the root, and then we get n plus 2 under the root in the denominator. Okay, so now that we've simplified that, let's try to apply the ratio test and see where this limit goes. Alrighty, so first step is trying to figure out what's going to be positive, what's going to be negative, and trying to distribute these absolute value bars appropriately. So anything underneath the square root is going to turn out to be a positive number, right? So since n is positive, this square root is going to end up being a positive value. The negative 3 is always negative, so we're going to have to change that to a positive 3. So in other words, I can kind of pop these two things out. Those don't really depend on the absolute value bars because they're already positive. I can also pop out the 3 as a positive 3. And the only thing I have to be mindful of is the x. So the x could potentially be a negative number. So depending on what value is chosen for x, we just need to be mindful of that. So this is kind of simplifying and distributing the absolute value bars. And actually, I'm just going to maybe rearrange this just a little bit just to make it look a little bit nicer, because we usually put the 3 and the x before the square roots, like so. Now this stuff doesn't depend on n, so we can actually pull that outside of the limit so that we can figure out where this limit goes. So let's move that 3 absolute x out and kind of take a look at what's happening with the limit of these two square roots. Now my guess is that this is probably going to tend towards 1. And I'm saying that because I'm looking at the dominant terms inside the numerator and denominator. So the dominant terms are n to the 1/2, or the square root of n, over n to the 1/2, or the square root of n. So what I could do is I could maybe apply L'Hopital's rule to figure this out, or I could maybe create a large square root, and because it's continuous, put that limit through the square root. I think that's probably the way to go. I could use continuity to essentially move the limit inside the giant square root and then use L'Hopital's rule. But I think it's easy enough here just to look at the dominant terms, the square root of n plus 1 and the square root of n plus 2. They're going to be growing at about the same rate as n gets really, really big. So this limit's going to tend towards the number 1. And so our limit overall comes out to be 3 times the absolute value of x. Now, because we're utilizing the ratio test, we want this limit to be less than 1 for absolute convergence. Okay, so now we're going to kind of start breaking this up into our interval of convergence and trying to figure out where things converge and diverge. So step 1. Let's find our interval of absolute convergence. Now, if our limit, which is 3 times the absolute value of x, is less than 1, we have absolute convergence. And this is something that we can certainly solve. We can divide both sides by 3 and get absolute x is less than 1/3. And then we can basically kind of expand this out, get positive 1/3, negative 1/3, and we have our radius, what we call our, our interval of convergence. I guess we don't have the endpoints yet, but I do have a little bit of information. I know as soon as I get to here, I have the radius of convergence. So the distance from the centermost point out to our boundary numbers should be 1/3. And this bit of information, well, this gives us most of the interval of convergence. So this gives us the interval of absolute convergence, but we do have to test those endpoints to see whether or not the power series is going to converge in the normal sense at these endpoints. So that's step 1, kind of dealing with finding the interval of absolute convergence. From here, I like to find where the series is going to diverge. So for any x values that are less than negative 1/3 or bigger than 1/3, we expect divergence. So anywhere outside of this absolute convergence interval, but maybe not the endpoints, we definitely have divergence. And step 3 is to test the endpoints. So let's take our first endpoint, which is x is equal to negative 1/3. And actually sub that into our original power series. And this was from 0 to infinity. Oh, my apologies. This should be a negative 1/3 up here. Okay, so let's plug in negative 1/3 in for x. And what we want to do is simplify this numerator a little bit. So let's take a little quick peek at this expression here. Because my guess is that we might be able to cancel some of these negative ones up here. So let's see. So I guess we could rewrite this negative 3 to look something like this. And we could technically write our fraction using power laws to look something like this as well. Right? So we could distribute the n to both the numerator and the denominator. And if we do that, these 3 n's will cancel. And in fact, we're going to get -1 times -1 for every single value of n. This is going to turn into basically just 1 to the n, or 1. So this numerator does simplify quite nicely, and it's going to simplify to 1 over root n plus 1. Now, this is a positive kind of series. This is probably a series that we can realistically solve using the integral test. So let's set up an integral from 0 to infinity of 1 over x plus 1 under the root dx. Now we could go ahead, we could use substitution, make this work, and I don't really see any issues with that. I'm just going to bump over to the integral calculator because I know this is going to be a little bit more involved than the last example, which is just working with the natural logarithm, just so we can kind of see what the antiderivative is for this one. So this is 1 over square root x plus 1. So let's see what the integral calculator gives us as an antiderivative. Okay, so here's our antiderivative, so let's roll with that. So 2 times root x plus 1. Okay, so taking that antiderivative, we're just going to be evaluating that at the endpoints. Remember that the upper endpoint, we just want that upper endpoint to tend towards infinity. We want that upper endpoint to get larger and larger. So we're really kind of thinking about a limit as this upper boundary value gets a little bit large. And what do we get when we sub 0? And I guess we're going to get 2 times root 1, which is 2. So we can see that this limit is going to tend towards infinity. This bit here does get very large as m gets very large. So with the integral test, we can see that this particular bound, this particular endpoint of -1/3 is going to be divergent. Okay, so that takes care of our first endpoint. Let's also sub in x is equal to +1/3 and see what happens. And then we'll have our full interval of convergence. So same kind of story as before. I want to maybe just do a little bit of work with this numerator and the powers here just to try to simplify this a bit. So I have something that looks like this. I'm again going to kind of favor writing it as -1 to the n times 3 to the n, and then 1 to the n over 3 to the n. So just distributing that n into the numerator and the denominator. And I do that just so that the 3 to the n's will cancel, and I can see kind of overall that I'm going to be left with a -1 to the n here. So this is going to turn into a series that looks something like this. And since this is an alternating series, we're going to tackle this with the alternating series test. And this one is going to converge. So our Bn is going to be 1 over n plus 1. And we're going to check the limit as n gets really, really big of just the positive portion here. And of course, this denominator gets very, very big, so this is tending towards 0. So this is going to converge by the alternating series test. So let's make a little summary of our findings here. We have a radius of convergence of 1/3. And we have an interval of convergence that's going to start at -1/3, go up to +1/3, and we just have to kind of be mindful of our endpoints. So at 1/3, I do have convergence, so we can use a square bracket here at that endpoint. However, at the other endpoint, we had divergence by the integral test. So there's our interval of convergence, and if you wanted to see this on a real number line, it would look something like this. This is technically a power series that's centered at 0 because it's x minus 0 inside of the absolute value bars or inside of the brackets. And then we ended up with two endpoints. We had a -1/3 and a +1/3. Of course, just putting open circles here. So everywhere inside of here was absolutely convergent. Of course, x is equal to 0 was our center. And notice that if we kind of measure out from the center, we have a distance of 1/3 in either direction. That's our radius of convergence. So that tells us where we should expect the endpoints to be, essentially. Now, everywhere bigger than 1/3 was divergent. Everything less than -1/3 was also divergent. We had a divergent series here. And in blue, I'm just going to put that we had a convergent series here. And it was convergent just in the general sense. So it wasn't, we can't guarantee that it's absolutely convergent because the ratio test doesn't give that, but it's going to be convergent in the general sense. So that's what our interval of convergence looks like as a picture. And we typically just summarize this with the interval of convergence from -1/3 and including the endpoint at 1/3. So there you go. There's a little ditty, a couple more examples, just kind of chatting about power series. I think hopefully we'll have a little bit of time on Monday next week, maybe to do one more example where we have an interval of convergence like this. And then we want to start talking a little bit about why we care about power series so much. Because they have some really, really nice properties that we're going to get to, hopefully by Wednesday's class next week. So the one last thing I wanted to do, just remind you of before you leave is the course evaluation. So if that's something that you would like to do, take a few moments just to evaluate the course. You're going to go into your Moodle shell and you're going to be looking for the evaluation of a college professor. So if you click on that, the little blurb will come up here. You should be able to find the survey link for winter 2021. And did I click that? There we go. So this should pop up something that you can kind of pop into here, and then you just want to search by my last name, and my last name is PenFound. So just kind of scroll down to where the P's are, and I am right here. So that's my name. You're going to click my name, and then my courses will pop up. Of course, you guys are calculus, so you can choose calculus, click the next button, and then the course evaluation will pop up. It shouldn't take too long for you guys to go through the course eval. Of course, I don't get these comments until after final grades have been released, and it's all anonymous anyway. I will not know who inputted any of this information. So, and I definitely will use this. I plan to teach some courses online in the future. So if there's anything that you think might be beneficial for me to know, kind of moving forward with online instruction, I would love to get a little bit of your feedback. So yeah, if you can do that before the end of day Friday, that would be great. Okay, so with that said, do we have anything else on the docket that we need to be mindful of? I think it's just the last quiz. So we have the last quiz and the last assignment. So the last quiz has been posted for you guys. So it's here, quiz number 10. So that one will be due by Sunday. And then the last assignment is still available until, I believe, next Friday. So those are the last kind of two big ticket items for you guys besides the final exam. And we'll have some time next week to talk about the final exam. I should hopefully be starting to get that all sorted out over the weekend. Okay, so with that said, have a great rest of your weekend, guys. And I will see you next week on Monday.